Look at this isolated biological brain floating in a sealed jar. It represents a modern large language model. It holds an immense amount of knowledge about physics, history, and code, but because it has no hands and no connection to the outside world, it cannot actually do anything. If you ask a standard chatbot to book a flight, it can only generate text telling you how to book a flight. An autonomous agent, on the other hand, takes that text, accesses a web browser, and physically clicks the buttons to buy the ticket for you. Giving a model the power to act on its own introduces serious risks. If you let an agent interact with your private databases or local files, you need precise control over exactly how it connects and what it is allowed to touch. This diagram shows the traditional way we connect AI to external tools. If you have 10 AI models and 10 different APIs, like GitHub, Slack, or a local database, you have to write custom code to connect every single pair. As you add more tools, this web becomes completely unmanageable. This is where the Model Context Protocol, or MCP, comes in. Instead of building hundreds of custom bridges, MCP acts as a universal adapter. It wraps all those traditional APIs into one single standardized connection that any AI model can plug right into. By understanding how to configure this protocol, you can build a secure, highly controlled bridge between your chosen AI model and your own private data. To make an AI use these tools effectively, we have to change how it thinks. A true agent does not read a prompt and spit out an immediate answer. It enters a cognitive loop to formulate a strategy first. This flowchart illustrates the 5 phases of an agentic workflow: plan, act, observe, reflect, and retry. The AI uses a tool, checks the result, and tries again. You don't hard code these steps. Instead, let the model decide its path, adjusting strategy from real-time feedback. A rigid script breaks when a website changes layout or an API returns an error. An autonomous loop detects the failure, reads the error message, and writes a new plan to bypass the problem. This schematic breaks down an MCP setup into 3 components: the host application, where the AI lives, the client managing the connection, and the server holding your local data. Inside the server module, the protocol provides 3 primitives: tools, resources, and prompts. Developers often think they must choose between using MCP to connect tools and using RAG to search documents. This is a category error. RAG is the organized filing cabinet retrieving data on the right. MCP is the glowing conduit wire carrying the AI's request. In a production environment, you do not pick one or the other. You build your RAG retrieval system to organize your documents, and then you wrap it inside an MCP server, so your agents have a standardized way to access it. Giving an AI the freedom to loop through actions until it decides a task is complete is incredibly powerful. It is also the main reason enterprise AI deployments fail. When models operate without strict boundaries, small errors compound quickly. This command line interface shows exactly what can go wrong. An AI hallucinated a policy, decided it needed to clear space, and executed a command to delete an entire production database, fully confident it was doing the right thing. To prevent mistakes like this, systems that handle high-risk tasks require a human-in-the-loop architecture. This timeline shows how that works. When the agent reaches a critical decision, the workflow halts at a red gate. The system saves the agent's memory as a checkpoint in the data layer, pausing indefinitely until a human gives the green light. Without that reliable state persistence to store the agent's memory during the pause, you cannot build runtime approval gates. And without those gates, autonomous agents are too dangerous to deploy in the real world. This JSON schema defines a tool for searching local notes. Step 1 in building an MCP server is defining exactly what the AI can do. Notice that we adhere to the principle of least privilege here by restricting the model to read-only access. Step 2 is writing the wrapper logic, connecting your local file system to the MCP protocol. Because the protocol handles the communication formatting, you do not have to write any custom logic for the language model itself. Step 3 is setting up your guardrails. You inject a risk score gateway that actively monitors the system. If the AI attempts to edit or delete a file, this gateway intercepts the request and routes it for human review. Finally, Step 4. You point your host application to this new local server and execute a natural language prompt to summarize a private document. By following these 4 steps, you take an isolated language model and give it secure, restricted permission to execute tasks on your personal hard drive. We started with a language model trapped in a jar, unable to interact with its environment. By implementing an industry-standard protocol, you built a bridge that allows it to execute real-world utility. This expanding constellation represents what happens when you scale this concept globally. Specialized AI agents securely connect across thousands of standardized applications, collaborating to research data, to write the code, and build complex software autonomously. The most valuable engineering skill of the next decade is no longer writing clever prompts. It is architecting the cognitive loops, building the persistent guardrails, and configuring the protocol connections that allow AI to safely operate in the real world.